All right, so we left off with this question. If we have a spring mass system and the force of friction is 0, what does that mean? So what do we have? We have our spring mass system. So we're assuming it's horizontal and attached to some surface here. We have some force of friction. And for our differential equation then, we're going to have mx double prime plus plus bx prime plus kx equals 0. And in the case of no friction, our differential equation now looks like mx double prime plus kx equals 0. And we're just going to make a guess. So here's the thing about differential equations. If you make a guess and it satisfies everything, then you're okay. And so we can use our intuition. And our intuition says we would expect to see oscillations. It's not clear how it's going to oscillate, but what's the most general thing we could do? And the most general thing for oscillations is we can try cosines and sines, but we don't necessarily know what cosine or what sine. So, for example, if I have sine of omega t, I can plug it in and see what's going to happen. So I'm going to have to be able to take derivatives of this thing. So the derivative of sine omega t is going to be cosine omega t times omega. And likewise, cosine omega t is also a possibility. So that's derivative of that's going to be minus sine omega t times omega. So what does this mean is that if I'm going to plug this back into here, and I'm going to have first and second derivatives, and because these things are going to switch back and forth, I got to account for both. So I'm going to just take a combination of both of these and see what happens. By the way, this is going to be useful later. Suppose I have e to the mt, where m's a constant. If I take the derivative of that, I'm just going to get e to the mt times m. If I have t times m to the t, from the product rule, it's going to be the derivative of the first, which is 1, times the second, plus t times the derivative of e to the mt, which we just said was that. So notice if I do this, I'm going to get something that looks like t e to the mt, but I've got this extra piece associated with it. Likewise, if I have t squared e to the mt, derivative of t squared is 2t e to the mt, and then the derivative of the second thing is still m e to the mt. So we're just using product rule. Okay. So when we're making these guesses and trying to make an estimate of what we think is going to happen, we've got to be aware of what's happening with these different kinds of functions. So if I have t n to the mt, and n is some fixed number, when I take the derivative, I'm going to have two terms associated with it. And so I'm going to have to be able to deal with those things later and figure out how do I make combinations of things that are going to give me the results I want. So it's really important to develop your intuition now about what are the derivatives of things like. And that's going to be very frustrating at first until you build up some experience. And just as a matter of completeness, derivative of a constant is 0. Derivative of t is 1. The derivative of t squared is 2t. Derivative of t cubed is 3t squared. So if I was told that the derivative of something is equal to 8 minus 6t plus 4t squared minus 18t cubed, I could just integrate it, but I could also note that because of this, it's going to look like something times t to the fourth. Right? But I still got to compensate for all the other things. So I could have something times t cubed plus something times t squared plus something times t plus something else and a constant. So I'm going to look at the highest order, try to account for that, but then I've got to add in all this other cruft in order to sweep up the mess afterwards. Okay, so let's come back to our spring mass system. And so I have what? I have mx double dot plus kx equals 0. And just as a matter of a guess, I can try x of t is equal to some constant times cosine omega t plus another constant times sine of omega t. And what I'm going to do is I'm just going to plug this in to my differential equation and ask what does it imply. And notice now that C1, C2, and omega are just constants, and I'm free to set them to be equal to anything I want. So if I'm going to plug it into here, I need to find the first and second derivative. Well, C1, that's just a constant. Derivative of cosine is going to be minus sine omega t times omega. That's just a constant. Derivative of sine is going to be cosine omega t omega. And then for the second derivative, I'm going to have minus C1. Omega just goes for the ride, but this becomes cosine omega t omega times omega, or omega squared. Here, when I take the derivative, I'm going to have derivative of cosine is minus sine, and the C2 just goes for the ride. I've got the omega just as a constant comes around, but when I take the derivative of this, I'm going to have omega squared. So if I plug this into my original dE, I have m times minus c1 omega squared cosine omega t minus c2 omega squared sine omega t. So that takes care of this part, plus k times x, and that's going to be c1 cosine omega t plus c2 sine omega t is equal to 0. So I'm going to ask, how can I make this true? So what I'm going to do, so we have m times minus c1 omega squared cosine omega t minus c2 omega squared sine omega t plus k times c1 cosine omega t plus c2 sine omega t is 0. So I'm just going to multiply everything through. So minus m times that, minus m times this thing. So that's this term. Now this term I'm going to multiply the k through. Multiply through by that one. So I'm going to have k c2 sine omega t is 0. I'm going to now collect like terms. So I've got two things that look like cosines. All right, and so for the cosines, I'm going to have this term plus that term. And now I'm going to collect all the other terms that look like sine. And now that's all 0. I'm going to leave the right-hand side alone. So I can factor out m c2 omega squared. Now I'm going to be careful, it's minus that, plus k c2. I'm going to rewrite this. So minus m c2 omega squared plus k c2 sine omega t is 0. Notice there's a C1 there and a C1 there, so I can factor that out. There's a C2 there and a C2 there, so I can factor that out. So I now have C1 minus m omega squared plus k times cosine omega t. I can pull the C2 out and have minus m omega squared plus k sine omega t is 0. Now I've got something times cosine plus something times sine is 0. The only way this can be equal to 0 for all time is if these coefficients are 0. And note I don't want C1 and C2 to both be 0. If they're both 0, right, what was my assumption? My assumption was x of t is equal to that. If both of these are 0, x is 0, and it's not going to be a solution. So that's out. So what is this? Says that minus m omega squared plus k equals 0. This one says minus omega squared plus k equals 0. So those are the same equations. If I add mw squared to both sides, I get that. So this is a solution if that condition is met. Issue is k was given to me. I can't change k. M was given to me. I can't change that. But omega was just some number I said I was going to fill in later. I can make that anything I want and not change anything. So this equation here uniquely determines my w, maybe. So let's see. If I solve for omega, I can divide both sides by k. Now I have to be careful. If I take the square root of this, I'm going to have two solutions. And the question is this two solutions? And the answer is no. The reason is there's a relationship between those two expressions. If I plug this or this into my original equation, cosine is an even function, so those are equal. Likewise, if I do the same thing with the sine function, this is an odd function, so if I pull that negative out, that's going to be the same thing. But since this is all multiplied by a constant, it's not going to change anything. So really there's only one of these solutions, and I'm just going to choose the positive one just because it makes things easier. What this says then is that my solution is going to look like some constant times cosine square root of m over k t plus some constant times sine of square root of m over k t. Okay. So let's look at an example. Suppose we have this situation. We've got a horizontal spring mass system, and we're going to construct it with a 2 kilogram mass. So m is 2. There's no friction, so B is 0. And we want there to be 3 oscillations each second. And the question is what's the spring? So the question is what value do we use for k? Well, we just showed that our solution looks like this. All right, so and let's see, we know that m equals 2, so our omega is square root of k over 2. And we want to figure out k, but we are given that we have 3 oscillations a second. So what does that mean? Well, if I have cosine omega t, and I know there's 3 oscillations per second, that means as t goes from 0 to t equals 1, omega t has to go through 3 cycles. And so there's 1 cycle every 2 pi units. So if I focus on this whole number, what goes into cosine, As it goes from 0 to 2 pi, there's one cycle. And as I go from 2 pi to 4 pi, there's a second cycle. And then as I go from 4 pi to 6 pi, there's 3 cycles. So this argument, the thing that I'm plugging into omega t, as t goes from 0 to 1, it has to go from 0 to 6 pi. And the smallest omega t can be is when t equals 0. So that gives me that. And the biggest it can be is 1, and then it has to equal 6 pi. So we get that omega has to be 6 pi. So coming back to this expression, we know that omega is 6 pi is equal to the square root of k over 2. And the question is what is k? Well, if we square both sides, we get rid of the square root. So k is going to be, multiply both sides by 2, k is going to be 6 pi squared times 2, which is 2 times 36 times pi squared, or 72 pi squared. Okay. Just a couple quick notes here. First note is going to be, this is going to be a little weird and it's not going to make sense at first, but as we go we'll see this more and more, is we need this idea of linear independence. And the idea is this, is if I've got functions y1, y2, y3 out to some yn, so each of these is some function of time. We're going to say the functions are linearly independent if the solution to c1, y1 plus c2, y2 plus c3, y3 on out, if that's equal to 0, that's only true, the only way that can be true is if c1 is 0, c2 is 0, c3 is 0, and cn is 0. And we already used this. And the way we already used this is we had something times cosine omega t plus something times sine omega t was 0. And we said the only way this can be true for every value of time is if this was 0 and as if this is 0. So this idea of linear independence is a really powerful idea. And this is going to be something that's going to pop up again and again and again. It's going to be confusing at first, but it'll start to make sense. All right. Last thing is I want to briefly discuss LRC circuits. And what's going to be important about this is it leads to a second order constant coefficient differential equation, and it's exactly, mathematically, it's exactly the same thing as a spring mass system. Okay, so this is an electronic circuit. And we're going to make use of Kirchhoff's laws. And the first law is around any loop, the total voltage drop is 0. This is basically conservation of energy. If you walk around any one loop in the circuit, the energy change is going to be, for an electron going around that circuit, is going to be a total of 0. And the other, you can think of this as kind of like conservation of mass. This is conservation of charge. And the sum of all currents at any junctions is 0. This is basically saying all the current that goes in is equal to all the current that comes out. Okay, and we're going to work with a couple different circuit elements. So these symbols are going to be important. First symbol is for a battery. Right? And across a battery, there's going to be a constant voltage change. And that's going to be in volts. So if you have a 3-volt battery, if you go across that battery, you're going to have a constant in time 3-volt change in the potential. Another thing is a capacitor, and the symbol for this is basically 2 parallel plates, and the voltage drop across a capacitor is going to be equal to Q over C. Q is going to be the charge in the plate, and C is a constant, and that constant is called the capacitance. You can have a resistor, which is basically a squiggly line. And the voltage drop here is going to be the current times the resistance. And this is Ohm's law. And in this case, I is the current, R is the resistance, and the R is generally going to be, for us, is going to be a constant. And the relationship between the charge and the current is that the current is the rate of change of the charge. And finally, we're going to have something called an inductor. So you're going to have these nice loopy things. And the voltage drop here is going to be some constant L times the derivative of the current. Okay, so L is called the inductance. If I could spell inductance, and that's going to be some constant. So battery voltage is going to be a constant. We'll call that some V naught. Capacitance, C is a constant. R is resistance is a constant. And the inductance, L, is a constant. So for example, if I want to refer to a simple LRC circuit, then it's going to have a battery, a resistance, an inductor, and a capacitor. So this is going to have some voltage, some resistance, inductance, and capacitance. And if I have one loop, if I go around, so if I start here and walk around, so if have an electron starts here and walks around, the change in voltage here is going to be V naught. The change in voltage here is going to, as it goes across the resistance, by the way, I'm just assuming a direction for the current. If I get this direction wrong, and I go through and work everything out, it'll give me a negative result. And I just have to interpret that as meaning the direction of the current is in the opposite direction I assumed. So just pick a direction. We're going to assume it goes this way and stay consistent. So as you go across the resistor, the voltage is going to drop. So this is going to be minus dq dt R, right? That's my minus IR. As I go across the inductance, again, I'm going to lose energy because I'm assuming the current's going this way. So if I have to push the electron across the inductor, it's going to lose energy. This is going to be minus L, and this is going to be the second derivative of the current, right? Because this is going to be, the second derivative is going to be the first derivative of I. And then finally across the capacitance, now we're going to pretend that the electron goes across. It doesn't really, but as you go across that inductor, the voltage drop is going to be minus Q over C. And so now when I add everything up, it has to equal 0. So I'm going to have V naught minus IR minus L times the derivative of I minus Q over C is 0. Oops, sorry. But I is going to be dq dt. I prime is going to be the second derivative of q. And then we just have q. And now I have a second order ODE because of that term. It's constant coefficient because V naught, R, L, and C are all constants. In this case, I've got a term here that does not have Q, so we will say it's non-homogeneous. If that V naught is 0, then we would say it's homogeneous. And we're going to explore situations at later times where the voltage can change. So be careful. We can ask what happens if the charge of my battery changes. For example, it might decrease over time. Then we can ask what happens. So we are going to focus on constant coefficient equations for now. And the very first thing that you need to do is when you see the equation is ask what kind of thing is it, and you need to be able to recognize it. So for example, if you are given this equation, you should recognize that it's second order constant coefficient. If you see something like, let's do this. Then you should again recognize that it's second order constant coefficient. And if you see something like this, this should be third. This is third order constant coefficient linear. Notice there's no initial conditions here given. So if we do give you initial conditions, I can expect you to deal with this and figure out what the constants are going to be. All right, so the idea is you're going to first find the general solution, and then you'll have two unknowns. Set up this equation, and then solve for the two unknowns. Same thing here. Here, because we have third order differential equation, when you go to undo this, you can think of this as doing three different integrals. You can have three unknowns, so you need three equations. So you might need information like this.